All right, let's take a look at our last one together for this video assignment on page 291. The total order and transportation cost, C of X, measured in dollars, of bottles of Pepsi is approximated by this function. X is the order size in the number of bottles in hundreds. Answer the following questions. Is there guaranteed a value R on the interval from 0 to 3? So if we were to have an order size of 0 bottles to 300 bottles, such that the average rate of change of cost is equal to the derivative of the function. So looking at the wording, okay, kind of hopefully it jumps out at you. We have the average rate of change. They're asking us, is it equal to the instantaneous rate of change, okay, meaning derivative. So that particular question is asking us about the mean value theorem, okay. Does the average rate of change equal the instantaneous rate of change, aka derivative? So it's a yes or no question. Is there guaranteed a value? It's either yes or no. So if it's that yes or no type of question, we essentially just have to check the criteria. Do the conditions of the mean value theorem hold true? Okay, are they satisfied based off of this equation and this interval? So for the mean value theorem, we have to check to see if it's a continuous function on this interval, but also differentiable on the open interval. So that would be from 0 to R, or 0 is less than R, which is less than 3. So we're not necessarily going to include the endpoints because we know a derivative doesn't exist at an endpoint anyway. So we got to think about, is there some value between 0 and 3, or including 0 and 3, if we're going to check continuity, that would make this function discontinuous? So at first glance, I see that we have fractions. Clearly, this x cannot be 0, and this x cannot be negative 3. So if we're checking continuity, we're going to have to check the closed interval, okay, where we have those endpoints available to us. And since this fraction would be discontinuous at 0, and that is a value within the closed interval, we would not be continuous at that spot. So since we don't meet the continuous criteria of the mean value theorem, we are not guaranteed a value such that the average rate of change would equal the derivative. So we'll say, since C of X is undefined at x equals 0, and this is within the interval, the mean value theorem does not guarantee a value R such that the average rate of change, I'm going to abbreviate this because I'm running out of room, such that the average rate of change would equal the instantaneous, aka the derivative. So there might be a value where that the average rate of change equals the derivative, but we're not guaranteed that there is one by this mean value theorem. All right, let's check out B. Is there a value R on the interval from 3 to 6? So now they're switching it up on us. So from 3 to 6, such that the derivative is 0. Okay, hopefully that's cluing us into Rolle's theorem. Give an answer and a reason, and if there is a value, find it. All right, so Rolle's theorem, we have to make sure that we're continuous and differentiable, just like the mean value theorem, but we have that extra criteria where the endpoints have to be the same. So looking at this function at the top, we said that 0 and negative 3 were the only values that would be an issue for us, but since we changed the interval, notice how those are no longer a problem. So we are continuous and differentiable. Okay, so we'll do check. Now we have to check the endpoints. So what is C of 3 and what is C of 6? So this is where we could use a calculator to probably help us out with this. 1 divided by 3 plus 3 divided by, if I plug in 3 there, that'll be 6. So 8, 3, 3, 3, and 3 is repeating. All right, let's go ahead and try 6 this time. So 1 divided by 6 plus 6 divided by 9. And looks like we get the same thing. All right, so all the criteria is met for Rolle's theorem. So we can say Rolle's theorem guarantees a value for R. Okay, so let's go ahead and try to find a value R such that the derivative evaluated at R is 0. All right, so somehow we got to find the derivative of this function. Now, depending on your shortcut preferences, you can attack this many different ways. What I might do, let's see, what if we were to distribute in that 10,000? It looks like we would turn that into 2 quotient rules. So our derivative, well, this one might be a little simple. If I go ahead and rewrite this, bring the x up, make it a negative power, I can change that into a power rule. So that one was pretty simple. But now this one definitely going to have to be a quotient rule because I can't really bring up that x plus 3. So we'll do, we need low d high minus high d low all over the bottom squared. All right, so this is our derivative. I know it looks like a lot, but we're essentially wanting to set it equal to 0 here and then solve for x, which is just going to represent this special value of r within the interval. So we know we should be anticipating some answer between 3 and 6. So if this is our derivative, I'm going to go ahead and set it equal to 0, and let's see, I really don't feel like solving this by hand, so I'm going to go ahead and use our calculator to help us with that. I'm going to graph it and try to find this value. So I'm going to go ahead and type in our derivative. Let's see, and then I'm going to add, okay, bunch of fractions here. X plus 3 times 10,000 minus 10,000x, and that's divided by x plus 3 squared. All right, and we're going to set it equal to 0. So for our window, I want to make sure that 0 is somewhere between the y's, so maybe I'll do -5 and 5, and my interval for the x's is somewhere from 3 to 6. So I know I can narrow it down to somewhere in here. And there we go. So we're going to go ahead and try to find that spot. Let's see, second trace, 0. Let's find this little cursor. There you are. All right, pick a point on the left, point on the right, take a guess. There we go. All right, so x equals, let's see, 4.0981 if you want to round it. All right, so there's our special value for R, guaranteed by this Rolle's theorem. So at this point, on this original function curve, we know we have a potential max or min, okay, because our derivative value is 0. It's essentially a critical point. All right, let's go ahead and check out the last one here. On the interval from 3 to 9, what is the greatest cost for order and transportation? So greatest, we're looking for an absolute max in this case. So thinking about our theorems, we're trying to find or use the extreme value theorem in this case. We already know that we are continuous on the interval, because 0 and -3 is not within there. So we're guaranteed a max or a min by the extreme value theorem, and that either happens at a critical point or an endpoint. So we have to check, or test rather, x equals 3 and 9, because those are our endpoints. We got to think about, are there any critical points within this interval as well? And that's where part B can kind of help us out. this 4.0981, because that's where our derivative was 0, and notice how that's within the interval as well. We also should be aware that -3 and 0 would be critical points, because that's where our derivative is undefined, but those aren't within the interval either. So we essentially have to check these three values. So C of 3, C of 9, and then C of 4.0981. All right, we got some calculator work here. I'm going to clear out the derivative function, and I'm going to go ahead and type in the original function, 1 divided by x plus x divided by x plus 3. I'll change my window from 3 to 9. All right, now, even though I can't see the graph, notice how it's done thinking. So it did graph it on this interval. It's okay if I can't see it, because I'm just going to go ahead and type in some values. So if I hit the trace button and then 3, it'll go to that point on the graph, but I just can't see it. So notice how we have that 8,333 number that we had before. All right, we'll go ahead and type in 9. And then 4.0981. All right, so they want us to find this absolute maximum, this greatest cost for order and transportation. And after evaluating the critical points and the endpoints, it looks like it's this 8611. This guy right there. Okay, so we'll go ahead and label this as the greatest cost.